Welcome to Physics 6. So what is physics? So first of all, it's a science. And what is a science and why is that so important? It's a process of trying to figure out how things work. You come up with a guess or hypothesis and then verify it by experiment or observation. Now this can be seen with Aristotle, the great Greek philosopher who hypothesized, he came up with a guess that heavy things fall faster than light things. But he didn't do the experiment. And it wasn't until a couple thousand years later when Galileo in Italy did the experiment and found that heavy things and light things fall at the same rate, with a slight allowance for air resistance. So the experiment is the crucial part of science. The first thing is to try to guess how something works, and secondly, to confirm that with experiment or observation. The reason we need verification, the reason we need that is because the human mind is easily fooled, like optical illusions and so forth. In the early 1900s in France, there was a physicist named Dr. Blondel, who was fairly well known, a legitimate scientist, and he believed that he had discovered some kind of ray, like an X-ray or gamma ray or something. And he had a box in his laboratory with various materials inside, and he thought that these rays were coming through a hole in the box, passing through an aluminum prism, and it made what he thought was a faint blue glow on a screen. He had other scientists come into his laboratory and confirm, oh yes, we see the faint blue glow. When you cover the hole, we don't see it. When we uncover it, we see the blue glow. And he was publishing papers and making a big deal that France had discovered N-rays. And then eventually an American physicist named Robert Wood visited Blondel's laboratory. They turned out the lights, put the material in the box, uncovered the hole, and Dr. Blondel said, Dr. Wood, do you see the blue glow on the screen? And Dr. Wood said, no, I don't see any blue glow. Dr. Blondel said, well, it's because your eyes are not sensitive and you're not trained to see such faint things. Dr. Wood said, no, I think the reason I don't see the blue glow on the wall is because while you weren't looking, I removed the prism from the box and it's in my pocket. So after a number of encounters like this, it became clear after Dr. Wood returned home and published his results, it became clear that the whole thing was just a sort of an illusion. The human mind is so powerful, it can cause you to see things that aren't really there. Dr. Blondel and his fellow scientists so badly wanted to be discovering a new ray that their mind was actually producing this sensation of a blue glow. Whenever you hear this double beep, it means it's time to go to the next slide. So now that we see that physics is a science, and just a reminder that the story of Dr. Blondel impresses on us how important it is to do actual experiments and observations. But what is it that sets physics aside from other sciences? Why is physics different from other sciences? What is it about, actually? Well, psychology, for example, is the study of the mind and behavior. But psychology is really based on the brain, which is actually biology. So psychology can theoretically be reduced to biology, the study of life. But biology is really determined by chemical reactions of various molecules, and theoretically biology can be reduced to chemistry, the study of molecular reactions. But chemistry involving the molecular reactions, molecules are just atoms with protons and electrons, which is physics. So chemistry can theoretically just be reduced to physics. But physics, what can physics be reduced to? Nothing is more basic than physics. For example, take the mass of an electron. Why does the electron have the mass that it does? Why does it have a charge of exactly +1? Nobody knows. It's a basic root fact of the universe. So physics then is the study of matter and energy and motion and light and electricity, but it's also the most basic of all the sciences in that it cannot be reduced to something uh, even more basic. So we've seen how important the verification and the experiment are in science, but verification involves measurement, and measurement involves units. For example, if you measure something to be 12 centimeters long, the unit is centimeters. If you ask me how long something is and I said 12, you would think, whoa, are you talking about inches, centimeters, or what? So the units are important. Whenever you write a number in physics, it's important to write the unit because that's what tells us what you're talking about. There are a lot of units in physics, but most of them can be derived from just the three basic units that we use: length, mass, and time. We'll be using the metric system, a specific kind of metric system that uses meters, kilograms, and seconds. That's the MKS system. So length is measured in meters, mass in kilograms, time in seconds. Sometimes we'll be using centimeters and grams. That's called the CGS system. But be sure to be careful that whenever you're using meters, you use kilograms, and whenever you're using centimeters, you use grams, and not to mix the two units up. You can read in the textbook the current definition of all these units. It's rather interesting, actually. The meter is defined as a certain number of wavelengths of light emitted by the transition of an electron in a particular element, and that's all described in the chapter. So what do you think? Is there any difference between 3 centimeters and 3.000000 centimeters? At first you might say, no, it's the same. They're both the same number. But there's a very important difference. If you go to a machine shop with a piece of aluminum, like an aluminum rod, and say, I want this cut to 3 centimeters, please, they'll put it in a vise and chop it off, measure it with a ruler, and hand it to you and say, that's 50 cents. 50 cents to cut it to 3 centimeters. But if you take the same aluminum rod to the same machine shop and say, I want this cut to 3.000000 centimeters, they'll say, well, leave it with us and come back next week. And then they'll send it out to a special lab that has laser interferometers and all kinds of fancy equipment to try to measure it to 6 decimal point precision. So that, and they'll charge you a lot of money for that. So the difference between all those zeros and not having those zeros is precision. It tells you how well you know the number, how precisely do you know that number, and that can cost money. So significant figures are important. It means more precision. Now, to count the significant figures of a number, you just count the number of digits, the number of numerals in the number. Like, for example, the one shown here, 0.00500. It's important to realize the zeros on the right-hand side of the decimal point are significant because the more of those you have, the more precisely you know the number. But the zeros in front of the 2 there are not significant. You could put as many zeros as you want. That doesn't mean you know the number any more precisely than before. It's only the zeros on the right-hand side of the decimal point that tells you about the precision. So here's a little quick quiz to check your understanding of significant figures. How many significant figures are in this number? Try to come up with a number before you go to the next slide to see the answer. And of course, there are 8 significant figures in that number. The zeros on the left are not significant. Those on the right are. It's important to pay attention to the number of significant digits, especially when you're working with lab data. The example given here is 278.3 times 47.008. When you're multiplying these numbers together, your calculator will show 13,082.3264. Now, the number 278.3 only has 4 significant figures. but the answer has 9 significant figures according to your calculator. Well, that means that a much greater precision than the number we started with, which isn't possible. So the answer can't have more significant figures than the number with the lowest number of significant figures on the left. So the answer needs to be rounded off to 4 significant figures, 13,080, and that number, the 1308, are significant. When you're adding numbers, it's a little different. You need to pay attention to the number of decimal places. So 123 plus 5.35, for example, gives 128.35, but the first number has no decimal places, so the answer must be 128. So when multiplying, you pay attention to the number of significant figures. When adding, you pay attention to the number of decimal places. And this would be a good time to stop and work out example 1.3 in chapter 1 of your textbook. A lot of times we'll be converting one kind of unit to another kind of unit, for example, centimeters to meters, seconds squared to minutes squared, whatever. There's a standard method for doing this, and it involves a conversion factor, which you can see here. The conversion factor consists of 2 parentheses with the actual conversion factor in the middle. So if you wanted to convert centimeters to meters, say 238.6 centimeters, the conversion factor would be 1 meter on the top, 100 centimeters on the bottom, because 1 meter equals 100 centimeters. That's really just equal to 1. But it's important to put the centimeters on the bottom so that they cancel out the centimeters on the top and you end up with meters. So what this tells you to do is to divide 238.6 by 100 and you get 2.386 meters. That's really important when you're converting squared or cubed units, that you square or cube the entire conversion factor. For example, 4,800 seconds squared converted to minutes squared. The conversion factor, of course, is 1 minute equals 60 seconds, with the seconds on the bottom, so it cancels out the seconds on the top. But notice the squared is outside the parentheses. That means everything inside is squared. The minutes are squared, the seconds are squared, and the 60 is squared. So what this tells you to do is to take 4,800 and divide it by 60 squared, which is 3,600, and that gives you 1.33 minutes squared. And this would be a good time to check your understanding of this by going through example 1.3 and exercise 1.3 in chapter 1 of your textbook. We're going to be using a lot of trigonometry in this class, so let's do a little bit of review of the trig. Sine, cosine, tangent has to do, of course, with the right triangle, say with sides x, y, and r, and in some angle theta. The ratio of the opposite side over the hypotenuse is the longest side, the opposite side of the angle in this case is y. The side y is opposite the angle. Opposite over hypotenuse, y over r, is defined as the sine of theta. And this ratio of y over r is the same for every right triangle that has these angles. The adjacent side, x over the hypotenuse, x over r, is the cosine of the angle. And the opposite over the adjacent side, y over x, is defined as the tangent of the angle. Now what if the angle theta was at the other angle up above there? Then what would y over r be? Well, if theta was the upper angle, y would be the adjacent side, so y over r would be the cosine, and so forth. And then we have Pythagorean's theorem that the hypotenuse squared equals the sum of the squares of the opposite two sides. R squared equals x squared plus y squared. For example, if x was 3 and y was 4 meters, what would the angle theta be? Well, the tangent of theta is y over x. So solving for theta, that would give us the inverse tangent of y over x. That'd be the inverse tangent of 4 divided by 3, which gives us 53.1 degrees if your calculator is set in the degrees mode. And just to be sure you've got a handle on all this, it would be good to stop and work out example 1.1 and exercise 1.1, or 1.10 actually, and exercise 1.10 in chapter 1 of your textbook. Okay, a lot of the quantities that we'll be dealing with in this class are called vectors. A vector is any number that has a direction. The direction is really important. Scalars, no direction. The reason this is so important is because vectors and scalars follow different rules for adding and subtracting and multiplying. So then, what do we really mean by vectors and scalars? Well, look at these following terms like temperature. Would temperature be a vector or a scalar? Well, if you say something has a temperature of 38 degrees, would you normally say it's 38 degrees north or 38 degrees to the left? No, a temperature doesn't have any direction. It's a scalar. What about distance? Now, at first it seems like distance might have a direction, but think about if you bought a set of tires with a 40,000 mile warranty and the tires wore out too quickly, and you take them back to the dealer and say, look, I only got 20,000 miles out of these tires. And the dealer says to you, well, what direction were you driving? You would think that was nonsense. But the dealer says, it's only warranted for 20,000 miles north. Any other direction, the warranty doesn't. See, that would be ridiculous. So the term distance, the tires don't care what direction you're driving. So distance is not, the direction is not important for distance. It's a scalar. But there are times when the distance does have a direction, but that's called displacement. For example, if someone tells you they want to meet you for pizza at the local pizza parlor and it's 3 miles from here, you'd have to say, well, 3 miles in what direction? Because the direction in going to the pizza parlor is important. So when the direction is important for distance, it's called displacement, and displacement is a vector. What about speed? Is speed a vector? Well, the next time a policeman pulls you over and says you were doing 90 miles an hour, just tell the policeman, hey, but I was going west. The policeman will say, it doesn't matter what direction you were going 90 miles an hour, you're breaking the speed limit. So for speed, the direction is not important. So speed is a scalar. But if you're trying to get to grandma's house and you're late, your speed does have a direction. It's important what direction you're driving to go to grandma's house at 60 miles an hour. So when speed does have a direction, it's called velocity. And velocity is a vector. What about time? Someone says, what time do you want to meet you there? And you say 4:15 west. Well, that doesn't make any sense. Yeah, time flows forward and backwards, future and past, but those aren't spatial directions. Time has no spatial direction, so time is a scalar. Another example of a vector is acceleration. Acceleration just tells you how quickly your speed is changing, and we'll see later on that acceleration is a vector. Other things are vectors too, momentum and so forth. Certain things not being vectors or energy. All this will become more clear later on as we look at these quantities. Just as a quick review, so we see that the vector has magnitude, that is how big it is, and direction. For example, speed is a scalar, it has only the magnitude, say 35 miles an hour. Whereas velocity, a vector, has a magnitude, 35 miles an hour, and a direction, say north. So why is it so important to differentiate between vectors and scalars? Well, it's because they behave differently. They add up differently. For example, if you look at the little triangle down there, you'll see that if you were to walk from your house 3 blocks east and then 4 blocks north, the distance you walked is just 7 blocks. That's how much your shoes have worn out. Your shoes have worn out 7 blocks worth of walking. That's distance. Doesn't matter what direction you are. But the other question is, where are you with respect to your house? That's your displacement. Your displacement is you add up 3 blocks plus 4 blocks, taking into account the direction. It turns out to be your 5 blocks from home. You would calculate that from Pythagorean's theorem, square root of 4 squared plus 3 squared, and so forth. So your displacement, which is a vector, is 5 blocks from the beginning, but it also has a direction, and the direction can be calculated just from the inverse tangent of theta. Theta is the inverse tangent of 4 over 3, which is 53.1 degrees. So your displacement is 5 blocks at an angle of 53.1 degrees, counterclockwise from plus x, or counterclockwise from east. There are certain properties of vectors that you should read about in section 1.9 in your textbook, and then work through example 1.11 and exercise 1.11 in your book. There are some interesting things we can do with vectors. You can answer certain questions like this question. If you look at the car driving sort of north of east or east of north, we can't say northeast because northeast implies 45 degrees, but it's going in some direction north of east. And if, say that car is driving 70 miles an hour at 35 degrees north of east, can we say the car has a velocity towards the east? In other words, is the car getting farther and farther east? Well, of course, the car is getting farther and farther east, so it must have some velocity towards the east, but it's not going east as fast as it's going forward. Look at the diagram and see if you can see that. So it must be going east at some speed, and that speed is called the east component of its velocity. So its velocity is 70 miles an hour, but it has some velocity towards the east. That's the east component. It also has a north component of its velocity. So how do we find how fast the car is moving east, its east component? How do we find that? So how do we find the components of a vector? For example, we have a vector A shown on the left, could be a velocity, for example. How do we find the component of that vector that's in the direction of x and the component that's in the direction of y? This corresponds to east and north in the previous example. The procedure, if you notice that the vector A is at an angle theta, the length of the vector represents its magnitude, go to the tip of the arrow, drop a perpendicular down to the x-axis. Now we have a right triangle. The side in the x direction is the x component of the vector, and the side in the y direction is the y component of the vector. Now remember that opposite over hypotenuse is the sine of theta. So opposite over hypotenuse is ay over a, which is the sine of theta. So solving for ay, we get a sine theta. So the y component of the vector a is just a sine theta. Remember that the adjacent side over hypotenuse is cosine theta. So the x component of the vector a is just a cosine theta. Divide both sides of that equation by a and you see ax over a, which is the definition of cosine theta. You got to be a little careful if anything is pointing to the left or down. If you look at the diagram on the right, if any of the components is pointing in the negative direction, then the component is negative. For example, in the right-hand diagram, the x component of a is negative a cosine theta because the component arrow is pointing to the left. The y component, however, is just A sine theta. To make sure you've got a handle on all this is a good time to work through example 1.12 and exercise 1.12 in your textbook. So how do you add vectors? And what does that even mean? Well, for example, suppose there was a cat running across the deck of a boat. And say the cat on the land, the cat can run 3 meters per second, say at an angle of 80 degrees, counterclockwise from plus x. In the meantime, the boat is moving with a speed of 2 meters per second at an angle of 30 degrees from counterclockwise from plus x. In that case, what would be the total speed of the cat? Now, it's not just 5. I mean, 3 plus 2 is 5. But those two velocities are in different directions, so they can't just add up. They're not scalars, they're vectors. Well, we can represent the cat's velocity with a vector in the xy coordinate system shown on the right, 3 meters per second, 80 degrees. And we can show the velocity of the boat represented in an xy coordinate system. So how fast will the cat can run 3 meters per second, but with the boat carrying it too, it's really going to be a little faster than 3 meters per second. So how do we calculate what that velocity actually is? So how do you add two vectors? We've got vector A, 3 meters per second at 80 degrees. We've got vector B, 2 meters per second at 30 degrees. How do you add them and find the resultant, the total speed, say, of the cat? The first thing you need to do is move vector A over to vector B so that it's head to tail. In other words, so the head of one vector is touching the tail of the other vector. This is the head to tail method of adding vectors. That's the method we'll be using in this class. Nice thing about vectors, you can slide them all over the place. You can change their position as long as they have the same size and the same direction. You can slide them around and it's the same vector. So once you get them head to tail, now we need to find the resultant, which is the vector from the very beginning to the very end. And now we can see what we need to do with this diagram to find the resultant of the vectors. Okay, once we have our head to tail diagram, we can work on finding the resultant of those two vectors. So here we have vector A, which is the cat's velocity across the boat. Down here we have vector B, which is the boat's velocity through the water. So all we need to do is find the components, the x and y components of these two vectors. Now we've already learned how to find components of a vector in previous slides. So we just need to perform the same procedure to find the components of these two vectors. So for example, for vector B, We drop it perpendicular to the x-axis. The horizontal side of this right triangle is the x component, and the vertical side is the y component. As we've seen before, the x component is just going to be 2 cosine 30 degrees. That's how long this vector is. And the y component will be 2 sine 30 degrees. So now we have the two components of these vectors that we're adding. The other vector, the components will be 3 cosine 80 degrees. That's this little vector right here. And the y component will be this vector, which is 3 sine 80 degrees. 3 meters per second at 80 degrees. So what do we do with those components to find the resultant? So now that we have the components of the two vectors, how do we find the resultant? To do this, you need to notice that the resultant here is a vector that has components. The resultant has an x component, rx, and a y component, ry. Now notice what with ry, if we swing over to the left here, notice that ry is just ay plus by. Can you see that in this diagram here? ay plus by is ry. So to find the y component of the resultant, we just need to add the y components of vectors a and b. Notice down here, the x component of r is just the x component of b plus the x component of a. If you add this plus this, you get this. So the x component of the resultant is just ax plus bx. So now that we have the components of the vector, we can find the vector itself. So let's do it. Notice on the right-hand side, you see rx equals ax plus bx. So we just add 3 cosine 80 plus 2 cosine 30. And if you do the calculation, you come out with 2.25 meters per second. Similarly, in the lower right, you see ry equals ay plus by. Just add them up and you get 3.95 meters per second. Now we know the components of the resultant, and all we have to do is put them together. Now that we know the components of the resultant, we can find the resultant itself. Notice that the components, rx and ry, are just the sides of a right triangle with r as the hypotenuse. So it's easy to find r. It's just the square root of rx squared plus ry squared. And if you do the math and plug in the numbers, it comes out to 4.55 meters per second. Now remember, the cat was running at 3 meters per second, but because of the boat carrying it along, it's actually moving faster than that, 4.55 meters per second. What's the angle that the cat is moving at? Well, ry over rx is just the tangent of theta, so solving for theta, we get inverse tangent ry over rx. And if you plug in the numbers, it comes out to 60.3 degrees counterclockwise from positive x. And you do need to specify where that 60.3 degrees is. In this case, CCW from plus x. So now we know the cat's total velocity, 4.55 meters per second, at the angle of 60.3 degrees as shown. Once again, you want to watch out for negative components. Here we have two vectors, one of which is leaning towards the left, so the x component of that vector b shown there is going to be negative. Be sure that when you add ax plus bx, you make that negative, so you get the correct component of vector c. Now the powerful thing about this head-to-tail method of adding vectors is you can add not only two vectors, but any number of vectors. In this diagram on the left, you see three different vectors that we want to add. Magnitude 3, angle 45 degrees, magnitude 6, 90 degrees, magnitude 5, 150 degrees counterclockwise from positive x. So all you have to do is move them over so they're head to tail. Look on the right there, you can see those same three vectors are now head to tail. The resultant will always be the line from the very beginning, down there at the bottom, towards the end. That blue line there From the very beginning of the vectors to the very end, that's the resultant. And to find that vector, all you have to do is start with the first vector on the bottom, find its x and y components. We know how to do that. Go to the second vector, find its x and y components. Go to that third vector at the top, find its x and y components. Add up all the x's and you got rx. Add up all the y's and you got ry. The resultant's magnitude will be the square root of rx squared plus ry squared, and the angle inverse tangent of ry over rx, just like before. You could add 100 vectors this way. It's always the same procedure. Line them up head to tail, find all their x and y components, add up all the x components, add up all the y components, Pythagoras theorem, inverse tangent, you got the resultant. We've seen how to add vectors. You can also subtract vectors. To subtract a vector, just make it negative. Turn it around so it's pointing the other direction, 180 degrees, and set a negative sign in front of its magnitude. And you just pretend like that's a vector that you're adding in your vector diagram. This whole procedure may seem a little complicated. I advise you to step through these slides again if you need to, but in order to really get it down so that it's an automatic procedure for you, you really need to practice. So I recommend working through examples 1.13 and 1.14 and exercises 113 and 114 in your book. And of course, the homework that I assign will give you more practice in adding vectors. And that concludes this PowerPoint presentation on Chapter 1 of the textbook.